Hello, everybody. This is for a course at the University of New South Wales. That's MATH2099, linear algebra section. And a few problem solutions that I would like to go through. That is related with the week 1. So in the question 5, we have a matrix, which this is a 2x2 matrix over the complex numbers. And we would like to calculate the A inverse. So there's another way of doing this by applying directly the definition. But let's do this way. So we put the matrix A, and then we think about the as augmented matrix. The matrix A here, and the right-hand side, we consider the identity matrix with the suitable dimension, of course. Since this is a 2x2 matrices, we are thinking about the identity matrix 2x2 matrices. Okay, first, the idea is exactly the same as we are doing in the over the real numbers. We would like to have the leading coefficients 1. So we want this position to be 1 and this position to be 0. This is our focus. So first, let's multiply the first row by minus I, which will make this position 1. Okay, then multiplying the minus I to this row will be 1 minus 3I minus I, and all the others will be the same. Now we focus on this position to be 0, so we add this row to this row. So row 2 is equal to row 2 plus row 1. So this will be 0, this plus this will be minus I, this will be minus I, and the 0 will not affect at all, that will be 1. Now we have this leading coefficient 1, we have this 1 is 0, it's perfectly good. Now we would like to make this position to be 1. So in order to be able to do that, if we multiply by I, we will have 1 in this position. So this is row 2, I times row 2. From here to here, the first row is exactly the same. The last row is my I times of these entries. That will be 1, that will be 1, and that will be just I. We are almost there. We want this position to be 0, such that we will have the identity matrix on the left-hand side, and we will obtain the right-hand side, the inverse, A inverse. So in order to be able to get this position is 0, we will multiply this by 3I and add to the first row. Then we will obtain the identity on the left-hand side. On the right-hand side, by multiplying this row with 3I, this will be 3I minus I, that will be just a 2I. This one by 3I will be just a minus 3, that is minus 3. So the inverse of this matrix is 2I minus 3, 1I. I think this is pretty straightforward. Let's have a look at another question. That is question 6. In question 6, we have a matrix 3x3 matrix. Any 3x3 matrix. And P matrix is given by with the columns. Columns, first column is a vector v1, second column is a vector v2, and the third column is a vector v3. And we suppose P is an invertible matrix. And these equations are given to us. AV1 is 3v1, AV2 is 2v1 plus 3v2, AV3 is equal to v1 minus 2v2 plus 3v3. This is all assumptions. We would like to find out, the question is, we would like to find out matrix M such that A times P is equal to P times M, and then we would like to show that M is unique. So this is actually pretty straightforward because these equations gives us the complete multiplication. So A times P is the matrix V1, V2, V2. If we multiply the matrix A with the P, then A times V1 is 3V1, A times V2, 2V1 plus V2, AV3 is V1 minus V3. So A times P is exactly this matrix given by these equations. Now, these are the vectors, right? These are the column vectors here. we can write this as a multiplications of two matrices. V1, V2, V3 is a row vector. And then I will just read it out with the columns, right? This is 3. If you multiply this row with this column, you will have 3V1, which is the first one. If you multiply this row with this column, that will be 2V1 plus 3V3, which is that one. If you multiply this with this one, you will have V1 minus V2 plus V3, which is that entry. So this is exactly just a matrix multiplication. I'm just writing down matrix multiplication in different ways. This is exactly this side, this AV1, AV2, AV3. And then I'm writing down this as another multiplications by thinking that by taking the P out on the left-hand side. And what else I can multiply with? I think this is pretty straightforward, just a matrix multiplication, as a matter of fact. So if the first part is just writing as a matrix multiplication will give you this result. So this matrix will be the matrix M that you're looking for. Now, in order to be able to prove that M is a unique matrix, suppose we have two matrices satisfying this condition, like AP is equal to PM1, AP is equal to PM2. Suppose we find two different matrices. We would like to prove that M is unique. So we would like to prove that M1 is equal to M2. Now, P is invertible. It is given in the question, right? P is invertible here. So I have two equations here, and P is invertible, which means that I can multiply this equation from the right-hand side with P inverse. And also, I can multiply from this side from the P inverse. And then P inverse from this side, P inverse from that side. What will happen if that case? So I will have P inverse here is equal to A. If I multiply P inverse from this side, I will have A. So this is what I'm saying here. So A is equal to PM1 P inverse, PM2 P inverse. Because as we know, P inverse means the identity. And if you multiply the identity with any matrix, will get you that matrix. Identity element means that X on as an identity, X on like a 1. 1 is identity element for the numbers system that you have. And the identity matrices is the identity element for matrix multiplications in the matrix vector space. Okay, so I have this equation now. So since I have IA is equal to Q on both sides, I have this equation. And then now I can reverse the order. So I can multiply this side from the P, and I can multiply P inverse from this side. From here to here, multiplication by P inverse from this side and P inverse from this side gave me the equality. I obtained this equality of these two sides, right? I obtained this equality. Now I am doing the multiplying P inverse and P from this side and P inverse this side, then I will get the M1 is equal to M2. This is my A. If I do that, P inverse from this side, P in this side, so I have identity, I have identity. So this is just M1. I have identity, I have identity. This is just an M2. So M1 is equal to M2. This is exactly what you wanted to prove in this question. Then M is unique. The M satisfying this condition, then M is unique. If you have two matrices, it's to be exactly the same matrix. It shouldn't be different. Okay. Let's move on to another question. Suppose A is invertible, and we would like to solve that A inverse is also invertible. And A inverse is A. I'm just going to start with writing the definition of invertibility. So A is invertible matrix. By the definition of the inverse of the matrix, what this means is that A times A inverse is equal to A inverse times A is the identity. Let's call this equation star. Now, we know that the inverse of the identity is identity. So identity is, there's no ambiguity of it. And if you have any two matrices, and if you're taking the multiply first and then you take the inverse of the multiplication, then it will be B inverse A inverse. This is a general fact, and this is a general fact, right? I can say. Now, we know those ones. Now we have equation star. I'm taking inverse in equation star. So inverse of this, inverse of this, inverse of this. The inverse of this itself. Inverse of this will be with respect to this rule. So this one will be coming first. The inverse of this, then inverse of this. So inverse of this will be A inverse because of this rule, right? This is the last one comes first. Last one comes first inverse. And the first one comes later. That's the inverse. For this part, I will have this one, right? So this is B is equal to A in this case. B is A in this case. That will be A inverse. And then the first one will be the last one when we take the inverse. So that will be A inverse inverse. This is the A inverse inverse. And the identity inverse is identity. So we obtain the equation 2. Right? So equation 2, if you think about it, this is, if you think that A inverse is the invertible because A inverse has a matrix satisfying this condition. So A inverse inverse is the inverse of A inverse, right? A inverse time A inverse inverse is the identity. A inverse inverse is identity. So this is by the definition, A inverse inverse is the inverse of A inverse. From here, you're applying the definition of the inverse. You're applying this definition, right? So you're thinking, I hope this is clear. Now, this equation and this equation together, equation star, equation 2 star, implies that A inverse inverse is equal to A. Because as you realize that this one will be this one, and the A inverse inverse will be the A inverse is this A inverse, and A is A inverse inverse. So it's just an equality. It is just I mean, just comparing the equation star and equation 2 star, it will give you immediately A inverse inverse is equal to A. So this is the follows from the just definition of the invertibility of a matrix. That's all. But this, to know this is important. You gotta know this. You gotta know this. You know, when you multiply two matrices, get an inverse of this multiplication, then the order reverse. That's an important bit. You gotta be very careful. You need to know this. You need to know this. Okay, let's move on to another question. That's question 8. Now, A and B are square matrices. And we say that A is similar to the B. And we write A similar to B if there exists an invertible matrix such that A is equal to P, B, P inverse. Right? This process is also called conjugation. So A and B are conjugate. In the matrix theory, that's what we call. Now, under this assumption, we would like to prove 3 properties related with this similar to operation. Now, similar to operations or similar to is reflexive. This is what we would like to prove. Which means, what is that? And this is the name of the property, reflexivity. Is A similar to A? We would like to prove that it is symmetric, and we would like to prove that it is transitive. Here, let's consider F is any field and I is the identity matrix. And let's do our proof under this assumption. Now, for each A in the matrices over n by n matrices over the field F, and identity matrix satisfies this condition. A is equal to identity identity inverse. So this is always true, which implies that A is always similar to itself. Symmetry. Now, for the symmetry, we will assume that A is similar to B, and we would like to prove that B is similar to A. Assuming A is similar to B, it means that exists an invertible matrix P satisfying A is equal to P, B, P inverse. This was a definition of the similarity, see? This is a definition that exists an invertible matrix P satisfying this condition. Just to define it, what is the similarity means? Assumption, what the similarity means. And now I got to do something about it so that I will obtain this property. So this will be other way around. So I must have something like a B is equal to something A, something inverse. There must be some invertible matrix satisfying this condition. So I can, since we would like to obtain the B, we can multiply with P over this side and P inverse over this side. So this is what I'm doing here, multiplying by P from the right and by P inverse from the left. That will be P inverse AP. So P inverse P and then B, P inverse B. So this is identity, this identity. So this will give me the just B. But as we know, just we proved actually, P inverse is P. Then we can understand this P inverse as P inverse a P inverse inverse. So the invertible matrix P is an invertible matrix. There exists an invertible matrix P inverse for this, such that B can be written in this format. Then B is similar to A, because this is by the definition. P inverse is invertible, then P inverse is P is invertible, then P inverse is invertible. And this is in the structure, as you see. Instead of this, we have P inverse, and it works. We found an invertible matrix such that we can write the matrix A and then the inverse of the invertible matrix. That will give us the B is similar to A. This is by its definition. I hope it is clear. Now the last property, transitivity. Transitive. So in this case, we will assume that A is similar to B, B is similar to C, and we would like to prove that A is similar to C. Right? A to B, B to C implies A to C. This is what we would like to do. This is the being the transitive. The property has a transitivity property. Okay. Now we will assume A is similar to B, B is similar to C. Then there exists an invertible matrix P and Q such that A, because A is similar to B, A is equal to some invertible matrix B and the invertible matrix P inverse. And then the B is similar to C means that exists a Q such that B is equal to Q, C, Q inverse. Now, by using these two equations, I need to obtain something like A is equal to some invertible matrix C and that invertible matrix is inverse. So by using these two. Now, if I substitute this B into here, this is what I'm going. A is equal to A is equal to P, and then I'm substituting B inside here. So I have P, Q, C, Q inverse, P inverse. Then I'm just associative, all matrices, matrix multiplication is associative. So I can change the placement of this bracket, not the order. Matrices are not commutative, but it is associative. Associative means that you can change this bracket places. I can place this bracket here like that, but I cannot change the order. I cannot PQQP. I cannot do that. Matrices are not commutative in general. It's very important. Okay, then this is PQ. Then I have C. And this one here, I have Q inverse, P inverse. But Q inverse, P inverse is PQ inverse. And this is very important. As I mentioned in the previous example, you have to use this all the time. You gotta know this. This is part of, this is important. You gotta know this. Now I'm using this equality here. I have Q inverse, P inverse, replacing with the PQ inverse. So this is exactly what I want. I'm writing the matrix A as some invertible matrix, C the inverse of that invertible matrix, which means A and C is similar. That's all I need. So A and C is similar. So that's all we want. B is similar, BC is similar, then AC is similar. Okay. Question 9. So this is like an algebra. We are going to do a little bit of algebra with some particular matrices. So if a matrix is symmetric, so these are all n by n matrices, square matrices. A is symmetric if and only this means that transpose of A is itself. B is skew-symmetric, which means that transpose of B is minus B. And C is orthogonal, means that C transpose is equal to C inverse. These are given to us. And then the question is to simplify this algebraically simplify these matrices multiplication. We are going to use these properties, the definitions of those ones, and we need to know a few things. What is the few things? First, matrices are not commutative in general. So you cannot change the order, right? You cannot say B, C, C, B, for example. It is not possible. If you have A times B as a multiplication transpose, that is B transpose A transpose. And also if you're taking the inverse, also the change to order. So AB, the whole multiplication inverse, will be the B inverse, A inverse. Okay, these are the facts that we are going to use to do some simplification for these equations. Okay, this is the first one. A inverse C B cube A transpose. Since we have the transpose here, that's the first thing we need to do. We need to apply the action of the transposition into the product of these matrices. So we are going to do this one. So the first one, well, the last one will come the first one. So this is A inverse. That's A transpose, B cube transpose, and then C transpose. That's that. And then this C is this one. Okay. Now, A is equal to A transpose. So this is what I'm doing here. B cube transpose. Let's leave it like that for a while. But C is an orthogonal matrix, which means that C transpose is equal to C inverse. On the other way of saying this is C transpose C will give you the identity matrix because we assume that we took C as an orthogonal matrix. Orthogonal matrix means that this multiplication is identity. So this is identity, this is identity. We only have B cube transpose. Now, B cube transpose means that you have B transpose times B transpose some B transpose. But B transpose is minus B because we assume that B is a skew-symmetric matrix. If you put minus B, minus B, minus B for each one, then you will obtain just a negative B cube will be the simplification for this equation. Okay, another equation. So A times B, A transpose. So this transpose needs to be dealt with first. So this will be A transpose, B transpose, because this is the product of the transpose. This is A transpose, B transpose here. B inverse here, C to the 6 here. I'll just write it down. And now you have a transpose here. You need to do it first. So this is C to the 7 transpose, which is here. And then B transpose comes later. Now, A transpose is equal to A because A is a symmetric matrix. So this is why I have A here. A transpose will be A. So matrices are associative. I can change the brackets in anywhere. I cannot change the order of the multiplication, but I can change the places of the brackets. So I can get this bracket here, B inverse. So this will give my identity. So I have C to the 6, C to the minus 7. So this will see, the powers will cancel out. I will only have C inverse here. And then B transpose, since B is the skew-symmetric, B transpose will be just minus B. Then here we have A square, B inverse identity. These powers will give me just minus 1. And then we have B transpose became minus B. And then we have minus B square. And this negative, which goes up the front, identity, just nothing disappears. And then C transpose is C inverse because C, it was the orthogonal matrix. This is why I replaced with the C transpose. We can leave it as a C. It doesn't matter. But this is the simplification that we got. And there's nothing else we can do, right? We cannot change the order of this multiplication because matrix multiplication is not commutative. Okay, the last equations that we would like to do. This is the equation that we have. We have inverse, we have transpose. So this will be C inverse, B inverse. This will be C inverse, B inverse. Since I have a C here, this will give my identity. Now, B inverse, B transpose is equal to minus B. This will give my identity. So I have A to the 5 here. That's A to the 5. Now the inverse here will be, again, the order will change. That will be A to the minus 4, A to the minus 4. This is why I have here A to the 5, A to the minus 4, and then B minus 2. That's B minus 2, right? I hope you're following up. And then I have C here. That C is this C. And then I have the transpose of this object. So that will be C transpose. That's C transpose, B transpose, A inverse transpose, A inverse transpose. Okay, C transpose is identity because C is an orthogonal matrix. B transpose is minus B because B is a skew-symmetric. And A transpose is basically A. So this is just A inverse. So the transpose and inverse operations can swap each other. So I can take transpose inverse is equal to inverse transpose. This is what I'm using here. So A transpose is equal to A. So this is just A inverse. So we can simplify now. This is identity. It disappears. This is identity, but we have a minus here because B is the skew-symmetric. B transpose is minus B. So B inverse will give us a minus identity. So this is why I have minus here. With the, right, this is minus, that's identity. minus identity is here, yes. And then here I have only A. The powers will cancel out. That's A. This A is this A. B minus 2 is this B minus 2. And then this identity disappear. So this minus B is this minus B. That's that one. And we have this one as A inverse. That's A inverse here. Now minus and minus will become plus. This will be A. And then we have B minus 2B. So one of them will make an identity B inverse. B will be identity. Then we will left with the B inverse. Then we have A inverse. So that's all we can do. That's all we can simplify. We cannot take this A inverse to the other side because matrix multiplication is not commutative. That's all we can do. There's nothing else you can do further ahead. This is the simplest form. Well, we can write it down like A is equal to A transpose. You can write it in some other ways as well, but there's no point. This is the simplifications for all of those. And key is that remind yourself, matrix multiplication is not commutative. You cannot change the order of the multiplication here. It's very important. Okay, I think that's enough for this video. I hope this will be helpful to you all. Thank you very much for watching it.